A triangular lot has sides of 450 feet and 570 feet. If the included angle is 100 degrees, find the length of the third side to the nearest foot and the area of the lot to the nearest tenth of an acre. If I'm finding the other side, and they have given me two sides, what they've done is they have given me that specific wording, included angle. So if I have 450 feet and then I have 570 feet, make it look like that. They are asking for the length of the third side. They have told me a couple things here. They have said those two side lengths and this angle measure. All right. So remember, when I have an included angle, I can't use law of sines, right? I have to use law of cosines. So law of cosine says if I'm solving for this guy, then c squared is going to equal the other two sides squared minus 2 times those other two sides and the cosine of the included angle. All right. That's where I would have gotten that from. All right. So to find your area here is your semi-perimeter. It's just S, right? So you find the perimeter and cut it in half. That's your S. And then you take each one of those and subtract your sides from it. Right? As usual, so when we're talking about polar coordinates, we are typically used to a Cartesian plane. We've added in an X, Y, and Z with three-dimensional, and now we're going to look at it in polar. So they mention air traffic controllers and a Doppler radar. So if you've ever seen a Doppler radar when they've just been talking about it, maybe on a news story or something like that, they look like these graphs, right? A Doppler radar looks like these graphs. And what they're basically doing is they're telling us a degree movement as well as an extension movement. So you can think of it, obviously this is why it would fall into our vector chapter. The way they write the coordinates, though, is a little bit different. And so we're still going to use the basic concept that we've done with the unit circle. Counterclockwise is going to be a positive theta. Clockwise is going to be a negative theta. Your R, that is going to be, think of that as like radius on coordinate plane. When R is positive, you're going to go in the same direction of where your terminal angle side would be. If your R is negative, you're going to find that angle and go in the opposite direction of where it would be. And so basically when I'm doing these, I will find my angle first and then find my R movement, okay? Whereas when you think of X and Y, typically you think X movement, then Y movement, right? When you're doing an XY coordinate. So I kind of do these the opposite when I'm graphing them, because which direction you go in from that angle is based on that R, and the R is listed first. So we're going to do an example of this, example 1, and then you'll see 3 different ones done with a positive and a negative as well on both sides. So let's look at this first example. A tells us to graph 4 pi over 3. Now, the one that I gave you is in degrees. You could have one of these in radians, or if it didn't put it down for you, you could write your own. This one is in degrees. So when I'm doing this, I would likely in my brain convert these to degrees, right? Just so I can think about on this particular one where I'm going. Pi over 3 is 60 degrees, right? And so I always track that first. If I'm doing my polar graphing here, I am going to start on my axis. This is going to be my initial right here. And so I'm going to have my initial right here at 0. And then I am going to track where this pi over 3 would drop me. All right, pi over 3 would drop me then at 60 degrees, all right? And so if my R is positive, I can go ahead and make that 60 degrees a solid line. But then I have to think about where that ends, because this actually has an ending point. The ending point is going to be at 4. And so if I look at this graph, 4 from the center is where I'm moving. So here's my center. I'm going to go 1, 2, 3, 4. So my ending point would be right here at 4. And that would be the coordinate 4 pi over 3. You can see that they dashed this, right? It keeps going, but the point itself is right there. You're talking about a specific point in place in space now. You're not talking about a vector, which has like a length and all. It basically gives you the length, but think about an XY. The X tells you how to move, the Y tells you how to move, but you're actually not drawing lines X and Y. You're actually just finding a point, right? And so that point is what we're finding on this polar coordinate system. So I always find my angle first, and then I decide where it's going to drop me off based on that angle. Let's look at the next one. All right. So if I do this next one here, if it will let me delete this and this alone, I am going to again start at the 0, but now it says negative 120. All right, so negative 120, I'm going to track clockwise here. All right, so I have to think of it backwards. This is going to be negative 90, right? Negative 120 is going to be 30 away from here, right? And so negative 120 is actually down here. Now, once again, I am going to draw this angle, as it were, right here. You can see I'm dashing it for right now. And then I'm going to decide how I'm going to move. 2. It's a positive 2, so it's in the direction of that angle. So I'm going to start from the center, and I'm going to say 1, 2. And I'm going to drop it right there. So it's going to end right here. It's going to look like that. So this is the point 2, negative 120, right there. 2, negative 120. All right. So a positive angle is going to move me counterclockwise. A negative angle is going to move me clockwise. And then we've done 2 positive R's. The positive R just says wherever it drops you off, you go in that direction. All right. Now we're going to look at a negative R. So let's look at the negative R here. All right. So if I do the negative R, I'm going to find my 3 pi over 4. And again, this is in radians. 3 pi over 4 is going to be a 45 over here, right? So it's going to be 135. So that's where I would think that I'm going to be, right? 135. You can see I'm going to dash this line to indicate where 135 would be, or 3 pi over 4. All right, that's my 3 pi over 4 angle. But I have a negative R this time, a negative R. So instead of going origin towards it, I'm going to go origin directly away from it, okay? So my negative is now going to move me away from my angle, not towards my angle. So I'm going to start at the origin, and I'm going to go 1, 2, 3 in the opposite direction. So this guy is actually going to be right here. All right, I'm actually moving 3 away from it because it was a negative R. All right, this is why I find my angle first. So this guy would be negative 3 pi over 4. Negative 3 pi over 4. Does everybody see how we're graphing these? Find your angle. A positive R moves you towards it. A negative R moves you away from it. You can see even when we did that second example, or that last example, where we went to positive 3 pi over 4, but then moved in the negative direction, there was another way you probably could have written that, right? If I went to 3 pi over 4 and went to the negative, I actually could have gone to negative pi over 4 and moved in the positive, right? And it would have actually dropped me off at the same thing. And so you'll find with these polar, just like with unit circle, there's more than one way to write it, all right? Remember unit circle. I could say 60 degrees, or I could say negative 330, and it would actually drop me off at the same spot on my unit circle, right? And the same is true for polar coordinates. you can look at these and you can see that these are all the same thing, but they're written different ways. This first one, 390 degrees and positive 3 movement. Well, 390 moves me all the way around, and then another 30. Positive 3 moves me 3 units towards that angle. I could have said negative 330. Starting here, going counterclockwise, negative 330 would drop me off 30 away from my x-axis, and a positive 3 would move me to the same exact spot. Positive 210. Well, positive 210 actually gives me exactly 180 degrees away from this right here, right? And now I could say, well, move in the negative direction, and I would still be dropped off at the same point, right? Same thing here. I could say negative 150. That would actually drop me off exactly opposite of that. And I could again say a negative movement. And you can see that all 4 of these would drop me off at the same exact place, What did we do here? Well, my reference angle here is 30. The original movement that they gave me in this was 3 and 30 degrees. All right, that was my original movement for all of these. What did they do for the first one? Well, all they did was add 360 to this guy. If I were in radians, I would add 2 pi, or I would convert it to degrees and add 360. The next one that they did, so here they added 360 to find an angle. The next one, what did they do here? Well, they just took that and they subtracted 360 right here from my original angle, 360, right? What about this one? So for these 2 right here, they took 30. And remember I said it's exactly opposite. When it's exactly opposite, it's going to form a line, okay? They're opposite rays. Well, what is the measurement of a line? It's 180 degrees. So for this one, what they did is they added 180 degrees. And then once they did that, that's how they got their 210. If you're going a complete opposite direction, we have to change the direction of my R. So they added 180 and they changed the R to the opposite, whatever it was. Change it to the opposite, right, of your original movement. For this one, they subtracted 180. So they subtracted 180 here to get my new angle measurement, my new theta. And again, they're in the opposite direction, so they changed the R to the opposite movement. So with unit circle, we would add or subtract 360 because we wanted to drop it off at the same place, and there really wasn't a movement situation with the unit circle. Here, we can do 2 different things. We can add or subtract 360, keep the R the same because that drops you off at the same exact place, or add or subtract 180 and flip your movement, flip your R movement to either positive or negative, the opposite of what it was. So there's actually multiple ways to do it when you're talking about polar coordinates, all right? All right, so if I take this negative 2 and I start with my circles, I subtract an entire circle, right? So I subtract 2 pi. I am going to get just negative pi, right? That's one way. If I add 2 pi, I'll be in the same place, but they actually gave me some stipulations here, right? So if I add 2 pi, I'm actually outside of the stipulations they even wanted. So you could write 3 pi there if they had not given you those rules of, hey, we only want negative 2 pi to positive 2 pi. Let's say I'm just doing across the 180, okay? So if I'm just adding or subtracting pi, if I subtract 1 pi from that, subtract 1 pi, where am I at? Well, I'm at 0, right? But I need to change this guy to a positive 2, right? And if I add pi to that, then I'm going to be at 2 pi, and I need to change that to a positive 2. All right? So if I look at where I am actually going to end up over here. So pi is right here, right? But then a negative movement actually moves me the opposite way. So I actually end up right there. So I'm trying to figure out how to end up there. Well, I can end up there at 0 with a positive, or at 2 pi with a positive, right? Or I can say negative pi, which drops me off here, with a negative. I still end up in the same spot on this polar coordinate. So we are accustomed to an XY type situation, not a polar coordinate. And so there is a relationship between polar and rectangular, which is what we're used to, the two-dimensional XY coordinate plane. And so there's a way that they coincide with the origin and the polar axis. And it's going to look very, very familiar, all right? It's going to look like your vector, all right? So if you are trying to figure out, well, what would this look like if I were to drop this off with an XY? You are going to use the same conversion that you would have used in vectors. You would take your r and you would multiply it by cosine of theta, which gives you your x. R times sine of theta, which gives you your y. Same conversion that we did in vectors, all right? Same conversion. And so it gives you a rectangular xy, and it tells you where it would fall if we were to convert it that way. Convert it that way with that type of movement. So let's look at this one. Convert the polar coordinates to rectangular coordinates. I'm going to take my r, which is 2, and I'm going to multiply it by the cosine of 2 pi over 3. And then 2 times the sine of 2 pi over 3. These are known on the unit circle, 2 pi over 3, right? That's a 60 degree in which quadrant? In the second quadrant, right? 2 pi over 3. So my cosine of a 60 degree is going to be negative 1/2. So I have 2 times negative 1/2, right? Cosine is negative in the second quadrant. And then my sine for a 60 degree is square root of 3 over 2. So I'm going to say square root of 3 over 2 there, right? Both of those denominators actually cancel out. And I'm left with a negative 1 and a square root of 3. That's fine. If they want it in rounded form, you would just put that square root of 3 into your calculator, right? So it'll tell you exact or round to the nearest, and you'll know whether or not you need to plug that guy in. But this is identical to our vector, all right? Identical to plopping it into vector. We're going to try one of those, and then we're going to convert the other way. 2 pi over 3, and then a positive 2, right? What that looks like if I were to do it in right angle. I would have moved negative 1 and up square root of 3, and it would have dropped me at the same point. It says find the polar coordinates for P, negative 5, negative 12, where R is positive and theta is between 0 and 360, okay? Between 0 and 360. So the first thing we have to do is figure out how far I'm traveling, pretty much. How far you're traveling is going to be the hypotenuse here, right? So if I'm trying to figure out my R, think about the trig on any point on the coordinate plane, right? If we were finding our r, we would just use the Pythagorean theorem, right? So to find how far I'm traveling along the hypotenuse, they have just given me my x and y value. They've given me my 2 legs of a right triangle, all right? So to find my r, I am going to just say, well, r squared is going to equal negative 5 squared plus negative 12 squared. They were nice. They gave me a perfect Pythagorean triple. 5, 12, this is going to be 13. R squared is going to equal 169. Square root of 169 is 13. Positive or negative, right, if I'm doing this. However, they told me which one I'm using, right? What did they tell me about R? R is going to be positive. So I know that my R is positive 13. That much I know. Now I need to figure out my angle. Well, angle is going to be using that x and y with inverse tangent, just like we've done every time to find angle, all right? Just like we would have done with a vector. So I am going to say, well, the inverse tangent of, and I'm going to just use my absolute values here, even though negative is going to give me a positive. I'm just going to say the absolute value of my y over my x, all right? Inverse tangent of that. If I do that, I'm going to get rounded approximately 67 degrees. I am not at 67 degrees. How do I know I'm not at 67 degrees? Well, I'm at a negative. I'm in the third quadrant. In the third quadrant, I have to add what to it? Yeah, so I have to take this and add 180. I am at 247 degrees, right? And so if you see what that looks like, I moved -5, -12. So if I'm finding how far down this I moved, that is my hypotenuse. That's why I did a squared plus b squared equals c squared, all right? 13 is how far I moved down it. That's also the first coordinate in my polar coordinate, all right? So when I write these polar coordinates, I will write it with that 13 first. And then the angular measure, it gave me the 67. That was my reference angle, right? In the third quadrant, I had to add that 180. It dropped me off at 247, and they rounded to 1 decimal place, but 247 is fine. So my second coordinate is going to be that 247 degrees. 247 degrees. And so I can convert the other direction as well. In example 3, I converted from polar to rectangular. In example 4, I'm just going the opposite direction, rectangular to polar. All right? In both cases, they have given us that r is positive, all right? You have to think about the fact if they told you r was negative, what would you do? Well, if I need to get to this point, but my r is negative, it means that my original angle would need to drop me off right here, right? And so my original angle would have been that 67 degrees, all right? 67 degrees, a positive 67 would drop me off right here. So if they wanted a negative r, I would actually leave it at whatever is the opposite. In this case, it happens to be my reference angle. It's not always going to be that. But in this case, I would leave it at 67, and I would have put a -13 there. All right, and that would have dropped me off at the same point, a -5 and a -12 movement, okay? So pay attention to these instructions, because if they tell you that r is negative, you're going to have to think about it differently as far as where your angle is, what your angular movement would be. All right, so look at right above example 5, right above example 5. The distance between 2 points described by polar coordinates can be found using the distance formula for polar. All right, you'll notice r1 squared plus r2 squared minus 2r1 r2 cosine of theta 2 minus theta 1. That looks vaguely familiar, right? That really truly looks like the formula that we use for law of cosines, which is where it's based on, honestly. Because if I were to draw this, and they have me sketching the graph here, so we'll draw it a little bit. The radar on a battleship detects ships at 15 miles, 140 degrees, and 27 miles, 240 degrees. Find the distance between the two ships, all right? And so if I were to sketch this, roughly sketch it, not beautifully on a coordinate, but if I were to do my polar, so to speak, and do 140, well, 140 is going to be approximately right here, right? About 40 away from there. And then 15, so I'm just going to estimate what that 15 would look like, all right? The other guy is 240. Well, 240 is going to be what? Another 60 away from my 180. So he's going to be down here, and he's going to be at 27, all right? And so he's going to be at 27. So this guy here is, let's say, 15, 140. This guy, 27, 240, all right? They want to know the distance between the two. Well, I'm actually finding from this point down to that point, right? Which means I need the angle in between, which I can find. And I can use law of cosines. That's why we subtract our 2, and that's why we're using law of cosines. We have the angle in between two sides, right? The angle given the two sides. And so that is law of cosines. And so I am going to say, well, to find this angle right here, I'm going to say, well, that angle minus this angle. That should give me what's left over. That's why I subtract those two. And so if I want to find that distance, I'm going to just plug it in. Well, that's going to be the square root of my 15 squared. That's my one side length squared, plus my other side length squared, minus 2 times my side lengths that I have, cosine of my enclosed angle, which is going to be the difference of those. So I'm going to say 240 minus 140 there. All right, that is law of cosines. That's all we're using there to find that, law of cosines. And when you plug all that in, they did round to 1 decimal place, approximately 33.1 miles. All right, you can see why this would be important information to be able to use, don't you think?